I'm not sure how much this overlaps with what Kuhn has done, but I think I've made it somewhat different. So what I'm going to talk about is unmeasured confounding, selection bias, and missing values.
Peter,
And
sorry to interrupt you.
yeah,
Actually, this part has not been really explained. So please
okay.
just all those things. Thank you.
Okay, so let's see here. So remember that I had defined causal sufficiency yesterday as a set of random variables is causally sufficient if the set contains every direct cause of any pair of variables in V. So in this example, if the set of variables is x, y, z, and this is the graph, then x, y, z is causally sufficient, but x, y is not, because there's a cause of z. I'm sorry, z is a cause of x and y, but it's not in the set. So in that case, if V is equal to X, Y's, that's not a causally insufficient set. So what I want to talk to, so this is basically, we're talking about not having confounders that are not in the set. So if we have unmeasured confounders, what I'm going to talk about today is how to deal with that problem. So let's start off with a couple of simple examples. Suppose that the true graph is the graph on the right, and according to d-separation, what we have from that graph is that x1 is independent of x2, x1 is independent of x4 given x3, and x2 is independent of x4 given x3. If I were to run PC on that algorithm, I'm sorry, there's a mistake there. The graph on the left would have directed edges from x1 to x3 and x2 to x3, and that should be a directed edge from x3 to x4. What I'm going to talk about, we'll show you in a couple of minutes, is there's going to be another algorithm which will give a separate representation. Instead of giving, however, a pattern or a CP DAG, which represents a set of DAGs that have no unmeasured confounders, it will be a graphical object that represents a set of DAGs, some of which may contain unmeasured confounders. So what it is ultimately going to do is to represent a Markov equivalence class of DAGs, only this time the Markov equivalence class is over DAGs that may contain unmeasured confounders, but we're not counting any unmeasured variables in the set of conditional independencies that's entailed. So I'll explain later what the one on the right means, but the one on the right says basically, well, we'll see later, it says that x1, that x3 is not an ancestor of x1. I can tell that from this arrowhead. But this circle means I actually don't know whether there should be an arrowhead indicating that x1 is not an ancestor of x3, or whether x1 is an ancestor of x3. And similarly, we have a circle there. So it's possible that x1 is an ancestor of x3. It's possible that there's an unmeasured confounder of x1 and x3, and it's possible that I would have that combination. However, the edge from x3 to x4, where I have a tail at the x3 end and an arrowhead at the x4 end, is telling me that x3 is definitely an ancestor of x4. And moreover, it's telling me that there's no unmeasured confounder of x3 and x4. So we're going to talk about how we can determine that. So an example of this would be something like, well, x1 is raining, x3 is the ground is wet, and x4 is that the pavement is slippery. So I could have multiple causes of the ground being wet, such as raining. X2 could be a sprinkler is on. Those could be, if I set the sprinkler on by a timer, then those are independent of each other, and they both are possible causes of the ground being wet, and X4 is slippery. So, how do I know that there's no confounding between X3 and X4? Well, suppose I actually tried to put in a confounder between X3 and X4. And suppose that that was an unmeasured confounder, so I had not measured C. In that case, we would see that the two of the d-separations that were entailed when there was no unmeasured confounder are no longer entailed. And that would be because x1 is deconnected to x4, conditional on x3, by the path that goes from x4 to x1 to x3 to c to x4. So what that would mean is that we no longer have those conditional independencies. So the original set of conditional independencies is simply not compatible with any unmeasured confounding of x3 and x4. If I were to run PC on this, then the output that I would get would be the graph on the left, and it would put in edges between x1 and x4 and x2 and x4 because they are not deseparated conditional on any subset of the measured variables. So in that case, what it would be saying is that x1 is the direct cause of x4, which is incorrect. So we can see that the output of PC has lost information if there's a confounder of x3, an unmeasured confounder of x3 and x4, because it can no longer tell the direction of the edge between x3 and x4. And it's also incorrect because it's added these extra edges which don't really exist. x1 is not a direct cause of x4, right? The graph on the left makes it look like if I wiggle x1 and hold x3 clamped, that I'll get some change in x4. But that's not what the true graph says. The true graph says if I wiggle x1 and hold x3 clamped, I won't get a change in x4. So it's messed up its predictions of what's going to happen when you manipulate. It's put in these extra edges. It's lost information. On the other hand, the graph on the right is what I'll explain in more detail later, is the output of the FCI algorithm. And it actually indicates, for instance, that it can't tell whether x1 is a cause of x4 because it has a circle up at the top here indicating it doesn't know whether there should be an arrowhead indicating that x1 is not an ancestor of x4, or a tail indicating that x1 is an ancestor of x4. And when we interpret it, we'll see that, as a matter of fact, the fact that there's a direct edge between two variables does not mean, should not be interpreted as indicating that there's a path from x1 to x4 that doesn't go through x3. That would be a misinterpretation of the second kind of graph, which we'll talk about later. So, so those are cases where, from the conditional independencies, we can tell that there's no confounder under the causal Markov and causal faithfulness assumptions. Now, we, as an actual example of this, in the 1970s, the Edison Electric Company in North Carolina was concerned about the effects of plant growth on acid rain. They took a bunch of measurements of the soil, and as well as the growth, and they got 45 samples of grass with all of these measurements of 13 variables. This was sort of the running example in a very standard textbook at the time about regression. In the textbook, he runs all kinds of different regressions on different subsets of variables and gets different answers all the time, and really doesn't know what to say about any causal relationships. If you run this through PC, you find that, as a matter of fact, the only direct cause of biomass was pH, and because it had one of these, what we call Y structures, which looks like a Y. From that, we were able to conclude that, as a matter of fact, the pH was a direct cause of the growth, and it was not confounded. That meant later they did some experiments on the soil and the properties of the soil, and verified that that was the case. Not because we said it was the case, but just because they were doing their own experiments. A second, so we've seen a case where we can tell where there isn't confounding. Here's a case where we can tell that there is confounding. So in this case, we have that x1 causes x2, x3 causes x4, and there's a latent confounder of x2 and x4. So L is assumed to be unmeasured. So among the measured variables, all we see is that x1 is independent of x3 and x4, and that x2 is independent. I'm sorry, x1 is independent of x. X2 is independent of x3. If we tried to run something like this through PC, we would have a problem, because it would make it look like that x1, x2, x4 was a confounder, and x2, x4, x3, was a V structure, and x2, x4, x3 was a V structure. But if I put V structures on both sides, I'd have a double-headed arrow. And PC doesn't allow you to put in double-headed arrows, so it would sort of have to choose that the arrowhead was on one side and not on the other side. But once it made that choice, it has made an error. It thinks, for example, that x2 causes x4 if it's not allowed to put in the double-headed arrow, even though it doesn't cause x4. So the basic situation here is that these three conditional independencies are not compatible with the d-separations in any DAG which contains only the variables x1, x2, x3, and x4. When you're in a situation like that, that's an indication that there could be unmeasured confounding. That in order to come up with a structure that has the right set of d-separation relations among the measured variables, you would need to include more variables in the system. In other words, unmeasured variables. So this could be the case, for instance, where if we're all attending the same lecture, x1 and x1 is I am not sick, x2 is I am in this lecture room, x4 is you are in this lecture room, x3 is you are not sick. So assuming we're not in the middle of our pandemic, and x1 and x3 are independent of each other, so we get sick separately, we both show up to the lecture room. And so whether we're in the lecture room depends on when the lecture is. So we would have a correlation between x2 and x4, a correlation between x1 and x2, a correlation between x3 and x4, and those are the only correlations we would have. And that's an indication that there's this unmeasured latent variable causing the correlation between x2 and x4, which is that we're all attending the lecture. So the PC output, as I said, would have to choose either pointing the edge from x2 to x4 or x4 to x2, whereas the FCI output would allow itself to put in a double-headed arrow, indicating that there is confounding going on. And there is no DAG without latent confounders that has the right set of deseparation relations. So let's think about different ways that we might deal with confounding. If I have the graph on the left, if I've measured L, then I could either do a constraint-based search or a score-based search. And in this case, I would come up with the correct DAG. Now, suppose, as a matter of fact, that L is not measured. What's going to happen to these DAG search methods? Well, we already talked about what PC would do. PC would make a mistake by putting an edge between Z and W, but having to orient it in one direction or the other. What if I did a score-based search? Well, if I did a score-based search, it would actually do something different than what PC would do. It would put in an edge and choose a direction for it. So it would either say it's going from W to Z or Z to W, but then it would have to put in an extra edge from, say, Y to Z in order to hide the fact that YWZ is an unshielded non-collider unless I put that edge in. So what that means is that it would choose sort of randomly one of these two graphs to output. And if you run an algorithm like FGES, that is what it does. It randomly chooses one of these two graphs as the output. So I'm sorry, it chooses the Markov equivalence of one of those two graphs as the output. So again, it also makes mistakes. So it puts in the extra edge from Y to Z, so it thinks that Y is a direct cause of Z. It thinks that either W is a direct cause of Z or Z is a direct cause of W. So it makes multiple mistakes. So they make incorrect qualitative predictions and they make incorrect quantitative predictions about manipulations. So you could say, well, okay, suppose instead of searching over the space of DAGs, as PC and FGS do, how about if I search over the space of latent models? So suppose I just allow myself to put unmeasured variables into the graph. And there are searches that are like that. So structural EM is a search which interleaves estimation of parameters with structural search. It typically starts off with you give it a starting graph, and then it tries to see if it can improve the starting graph by putting in extra unmeasured variables and more edges. But there are very substantial computational and statistical problems if I'm directly searching over the space of latent variable models. There are going to be ways of dealing with some of those issues that we'll see later in the linear case in particular, But in the more general case, it is quite difficult for the following kinds of reasons. So let's think about DAG models that don't have latent variables. They have a lot of nice properties that people like, which is why they're using them. They provide a finite search space, and they have a whole slew of really nice statistical properties. They're always identified. They correspond to a set of distributions characterized by independence relations. They always have a well-defined dimension. They have asymptotic existence of maximum likelihood estimates. So all of those things are really quite desirable statistical features of a model. But once we introduce latent variables to the model, a lot of those nice statistical features go away. We no longer have a finite search space because I can just keep adding latent variables. Again, there are some ways you can try and limit that, but it certainly complicates the search. It also means that they're not always identified. So I can't tell necessarily which is the right latent model given the variables, the measured variables that I have. There are going to be other constraints on the marginal distributions that are not conditional independence constraints. So what I mean by that is, suppose I start off with a model that is completely characterized by conditional independence constraints, and then I take the marginals of that set of models. Well, the marginal of that set of models can actually have non-conditional independence constraints, and we'll see examples of that later. If you if you look at the set of marginal distributions of a model that is even Gaussian, as nice as a Gaussian model, it turns out that the space of probability distributions that you get by taking that marginal has all kinds of weird features. It doesn't have a well-defined dimension. It doesn't have asymptotic existence of ML estimates. So you have a lot of theoretical problems, as well as having a lot of actual problems, in that you can show that in many cases, for instance, the BIC score is no longer good at picking out the correct model. So what my colleagues and I did was to say, well, we won't deal with the set of marginal distributions of a particular latent variable model. What we will do is to only look at the conditional independence constraints on the observed variables. Now that set of models, the models that only look at the independence constraints, are models that do have a lot of nice features, and we can use those nice features to make search much easier, and to give the models a lot of nice properties, so that, for instance, there will, in many cases, be ML estimates that we can do. So basically, if this sort of ragged-looking thing here is the set of marginal distributions of a given model, what we would do is to say, well, because there are non-conditional independence constraints imposed, then what we would do is to say, well, we're only going to look at the conditional independence constraints, and so we will embed this kind of raggedy model into a bigger model, which doesn't worry about the other constraints that might hold, and use that in order to do all of our searches and our predictions about the effects of manipulation. So we'll see a more concrete example of that in a minute or two. So, so let me just say, if we step back and move to a higher level, we can think that we are really dealing with 4 different kinds of models simultaneously. We are dealing on the one hand with a graph, which is just an object with a bunch of vertices and a bunch of edges. We're dealing with an independence model, which is a bunch of independence relations that we have associated with the graph. If the graph is a DAG, then the independence relations that we have associated with the graph are just come from D-separation. We also have a probability model because we are representing a set of probability distributions, and we have a manipulation model because we are using the graph to tell us about the effects of manipulations. So in the DAG case, we have directed acyclic graphs. We use D-separation to figure out what the independence model is. We use the do calculus to tell us what the manipulation model is, and the probability model is going to depend upon what class of family of distributions we're interested in. So let's suppose that we start off with our nice DAG models and everything's very clear and everything's fits together nicely. And ask ourselves, what happens if we marginalize the independence model? Well, when we marginalize the independence model, in this case, I'm taking L to be unmeasured. I simply cross out all of the conditional independencies that involve L, right? They're no longer part of my model. So I'm not saying they're false. They're just dropped out of the model. They're not even mentioned. What I would like to have, and what I don't have with DAGs, is that I would like to have a DAG in which I could marginalize the graph and get out a graphical object which represents that marginal independence model. The problem is there is no DAG over X, Y, Z, and W which has that feature. So what I have to do is to expand the set of graphs that I'm looking at. So I'm going to create this new kind of graph, which is called a maximal ancestral graph. And I'm going to define a new kind of an extension of D-separation, which is called M-separation. And I'm going to associate an independence model with that graph using M-separation. M-separation is just going to be the most natural extension of D-separation that you can think of. It simply allows for double-headed arrows, and everywhere that it talks about colliders, it just means it's anywhere in the graph where I have 2 arrowheads coming together. So XZW is a collider. Even though this is not a directed edge, it's a bidirected edge. And YWZ is a collider. So remember that what the problem that PC had was that it couldn't have colliders on both sides, even though it wanted to. But with a double-headed arrow, I now can do that. So what I can do is to take this new concept of M-separation and say, this is my original graph. I'm going to define an operation on marginalizing the graph so that it looks like this graph. And then I'm going to say that the M separations in this graph give me the marginal of the independence model. So what I've done is I've given an operation on how to marginalize an independence model. I've given you a parallel operation on how to marginalize a graph, which turns one graph into another graph. And then I've hooked those two up so that if the original graph represented the independence model via d-separation, then the marginalized graph will represent the marginalized independence model through n-separation. And the nice feature of this is that I can then take this graph and apply my marginalization operation again. And if I do that and I apply m-separation to it, I will get the correct marginalized independence model. So basically what I'm saying is that these graphs that I'm defining are closed under the marginalization operation. That is, I can just keep marginalizing them, and every time I marginalize them and apply m-separation, I get an independence model. And the independence model that I get is just the independence model that I get by applying the marginalization operation to the original independence model. So I'll skip these. This is basically what I just told you. That's basically what we're going to be doing. So we're going to create a new class of graphs. It is in some sense going to be the marginal over the set of observed variables of the original graph, and it's going to hook up to the independence model in the way that we want. By applying m-separation to our maximal ancestral graph, we will get the marginal of the d-separation relations from the original graph. Then we're going to, you can also use those graphs and get a manipulation model and a probability model out of them as well. So we're going to have a new kind of graph. It's going to have, it's a new kind of graph. It'll have an independence model associated with it. It will have a probability model associated with it, and it will have a manipulation model associated with it. So let's look at these two graphs, G1 and G2. In my, suppose, let's look at G1. Each vertex is independent of its non-descendants given its parents. So the independence model is simply that x1 is independent of the other observed variables x2 through x4 given t. And similarly, for every observed variable x1, x2, x3, x4. That's my independence model. And the probability model I could get, this would be via structural equations. I could say that x1 equals a times t plus epsilon 1. And then I have my 5 equations. And then I could also simply assign real values to A, B, C, and D, the variances of the error terms, and then I would have a multivariate Gaussian model. The first thing I want to tell you is to understand that if I marginalize T out of this model, then, well, actually, let's not even marginalize T. Let's just say that the margin, if I look at the marginal distribution over x1, x2, x3, and x4 of the set of distributions that I could get out of this graph using these equations, there's actually a non-conditional independence constraint imposed. And it's this constraint here, that covariance x1, x2 times covariance x3, x4 equals covariance x1, x3 times covariance x2, x4, which equals covariance x1, x4 times covariance x2, x3. This is what I mean by, if I took the set of distributions compatible with this DAG over all 5 of these variables, and then I took the margins, the set of distributions I get by marginalizing T out of that original set of distributions, all of them satisfy this additional constraint. So that means that there are non-independence constraints entailed by this marginalization operation. So even though in the original graph, all of the, as long as I'm doing a Gaussian linear model, I can completely characterize the set of distributions by conditional independence relations. This set of distributions, which are the marginals of those distributions, cannot be characterized just by independence constraints because they have this kind of non-independence constraint that's imposed as well. So the manipulation model basically says, well, I'm just going to take my original set of equations and I'm going to replace my equation for x1 by setting x1 equal to a constant, and that's actually not going to do anything to any of the other variables, right? Because x1 is an effect of t, it has no, and if I manipulate it, it's not a cause of any of the other variables. So I would end up with the same set of equations, and the mean of x2 would be equal to 0 still. On the other hand, I could flip that edge and go from x1 to t, and I would have, in that case, if I were to manipulate x1, then it would have an effect on x2 because I would have the path x1 to t to x2, and the mean of x2 would no longer be 0 if I manipulate x1. Okay, so the marginalization model, if I start off with this original model, it's just empty. There aren't any. So this would basically, what this here means, this operation, this symbol here means I'm marginalizing out the latent variable, and this is the independence model associated with G1, where I've marginalized out L. And that is what I would get, which is just there aren't any constraints. On the other hand, if this were my original graph, and I were to marginalize out T from the independence model, I would just cross out the sole conditional independence that involved T, and the other two would be left. Okay, so this maximal ancestral graph that I'm going to construct, it represents a set of the graphs that share certain ancestor relationships. So I'm going to take G, I'm going to take the Markov, the I equivalence just means Markov equivalence. I'm going to marginalize those graphs, and they will share certain ancestor relationships. So let me give an example here. If this is my graphical model and I perform the marginalization operation, then what I would get is the graph on the right, which is a maximal ancestral graph, and it has double-headed arrows everywhere. So I've removed T, and it's got double-headed arrows everywhere, and this means that x1 is not an ancestor of x4, and x4 is not an ancestor of x1, and x1 and x4 are deconnected conditional on every subset of the other variables. And similarly, that would be true for every pair of variables. So that would be the graph that I get. And if I had a second latent variable T2 and I performed the same marginalization, I would get out the same marginal graph. So just as many different distributions can have the same marginal probability distribution, many different original DAGs can have the same marginal graph. So how do I form this? Well, there's an edge between any pair of variables if and only if The only way to deseparate them in the original graph, where this means that A and B are deseparated conditional on C, there's a latent variable in C. In other words, the only way I can deseparate them is using a latent variable, and so when I marginalize the independence relations, that deseparation relation is dropped. If they're adjacent, then a single directed edge means that A is an ancestor of B, and if they're adjacent, then a double-headed arrow means that neither one is an ancestor of the other. So if I form the graphs in that way, then in this case, that would be my, so in this case, this would be my independence model, and well, I'll show you the graph in a minute. The graph should be, sorry, where did it go? I'm sorry. Yeah, that got removed. Sorry. It's okay. So in this case, there would be a directed edge from x1 to x4 when I did the marginalization, and that is because x1 and x4 are deconnected conditional on every subset of the observed variables. The only way I can deseparate them is using T, and the reason it would be a directed edge would be that x1 is an ancestor of x4. So it's important to recognize that we have this operation, which defines the mixed ancestral graph. And what does that graph represent? Well, that graph represents a subset of the graphs in the equivalence class to the original graph that share certain ancestor relationships. So in other words, everywhere that I have an edge that's directed, it has to not only represent the same set of conditional independence relations as an equivalent graph, it has to have the same ancestor relationships as the original graph. It doesn't represent the set of marginal distributions of DAGs that are Markov equivalent to the original graph. And that is, again, because if we remember that we had those non-conditional independence relations that hold in the distribution, and those are not represented by the marginal graph that I create. In the Gaussian case, the parameterization of the marginal graph is simply that of a particular kind of structural equation model, which and structural equation models do allow you to have double-headed arrows. All the parameters are identifiable, and the maximal ancestral graphs are closed under marginalization. You can score them for certain families of distributions in the usual ways fairly efficiently. It's important to recognize that not every parameter is directly interpretable as a structural coefficient. That is, they can be used to tell you what the distribution is, but they can't be used to tell you what the effect of a manipulation is. And I'll show you an example of that in a minute. Not every part of the marginal manipulated model can be predicted from the mixed ancestral graph. So sometimes I can predict what the effect of a manipulation is if you give me the mixed ancestral graph, but sometimes I can't. So let's let me just say a word about M connection in a marginal ancestral graph. A path between a pair of vertices in an ancestral graph is said to be M connecting, giving a set Z, possibly empty, if every non-collider on the path is not in Z, and every collider on the path is anterior to Z. That is, there is a path from there's a path from X to Z where none of the edges points towards X. So it is a very natural kind of generalization of D-connection. It's just slightly different because now we have double-headed edges as well as directed edges, and those double-headed edges can everywhere two arrowheads come together, we just call that a collider. So we have patterns of colliders that we can't get in a DAG. And then we have this idea, just as in the DAG, if they're in order to be deconnected, every collider on the path has to have a descendant in Z. Here it just has to be anterior to Z, which is very close to the same thing. It's just that that you can't have any edges pointing backwards towards the collider. It's important to recognize that the edges, you can get edges in sort of peculiar situations which don't intuitively represent what you think they're representing. So if we look here at the graph A, what you would see is that even though there's no edge between gamma and delta, if we apply M connection to this object, what we see is that gamma and delta are M connected given every subset of alpha and beta. So that's quite different from a DAG. In a DAG, that can only happen if two variables are adjacent. But in our mixed ancestral graphs, that might not happen. However, what we're going to do is to say if they are not M separated, conditional on any subset of the other variables in the graph, we'll just add an edge to the graph. So in this case, we would add gamma, the double-headed edge between gamma and delta, which says that gamma is not an ancestor of delta and delta is not an ancestor of gamma, and we can always do that. So note that multiple DAGs have the same marginal graph. So if this is my true graph and T is an unmeasured confounder, and I want to marginalize T out, what am I going to get? Well, the mag that I'm going to get is just going to be that. It's going to be a directed edge from X to Y because remember that the directed edge simply means that X is an ancestor of Y. Unfortunately, that looks just like G2, which doesn't have confounding. So that means that both G1 and G2 have the same mag. They have the same X to Y with a directed edge between them. So this is a case where we have multiple DAGs with the same marginal graph. Now, there are alternative representations of marginal graphs. So instead of forming a mag, we could form something which is quite commonly used, which is an acyclic directed marginal graph. And it solves this problem about what to do when there's a confounder of X and Y and a directed edge between X and Y, simply by saying, well, if it's G1, then what I'm going to do is just put in a double-headed arrow to represent the confounder. And I'm going to also put in a directed edge to represent the directed edge. I can, again, define an extension of D separation, which works for ADMGs. The problem with this is that while it's more informative, because it distinguishes between G1 and G2, the ADMG for G2 just is the same as G2. It's more informative, but it's not identifiable from the data. The data is not going to tell you whether you should have the ADMG which contains the double-headed arrow or it doesn't contain the double-headed arrow. So for that reason, we're going to stick with MAGs. Now, MAGs are not quite identifiable because in addition to there being multiple DAGs compatible with the same MAG, there are multiple MAGs compatible with the same independence model. And we'll see that in a little bit. So here we are, I've shown you what the graph is like. It's basically just a combination of directed edges and bidirected edges. There's at most one edge between any pair of variables. We've seen that D connection can be extended in a natural way to M connection. You can estimate the parameters in such a way that I can tell you what probability distribution is represented by the MAG. But what is the manipulation model associated with a MAG? Well, there are going to be two kinds of cases. There are going to be, in some cases, if I give you a MAG, then every single directed acyclic graph compatible with that MAG, that is, which has that MAG as the marginal, will predict the same effect of a manipulation. And in other cases, it won't. So that we only have a partial manipulation model. We have that sometimes if you give me the MAG, I can tell you what's going to happen when you do a manipulation. And in other cases, when you give me the MAG, I won't be able to tell you what happens when I do the manipulation. So this is the case we looked at earlier. This is the marginal of the case where there was a unmeasured confounder between A and D. So that would be one DAG that has this marginal. Another DAG which would have this marginal is simply just the DAG where A really is a direct cause of D. So I would have two different DAGs, and they would both have the same marginal. And if I asked you what happens when you manipulate A, well, they give two different answers. One of them says, well, when you manipulate A is really is a direct cause of D, and the effect, if I estimate the effect of A on D, then using the parameters that I assign to this MAG, I would get the correct answer. On the other hand, if the other DAG was the truth, and instead of having a direct edge from A to D, I had an unmeasured confounder between A and D, and I had the same MAG and the same parameters, it would give the same answer, but the answers ought to be different because when I manipulate A here, this path affects D, and when I manipulate A and there's an unmeasured confounder, that no longer it has an effect on D. So I would get different answers. On the other hand, because I can't tell whether there's an unmeasured, here I have a directed edge, but I don't know whether there's also unmeasured confounding or in place of this, unmeasured confounding of A and D. But remember, earlier on, we saw that there can't be any unmeasured confounding of C and D. So since there can't, because if I put in unmeasured confounding of C and D, I have to change my independence model. So because there can't be any unmeasured confounding of C and D, what I end up with is that I can tell what happens when I manipulate C, what its effect on D is going to be. The effect of C on D is just going to be the parameter that is associated with this edge, C to D, because manipulating C is not going to affect D through any other path going through A, because it's not an ancestor of A. So that's not going to happen. It's going to affect C to D through this path here, and there's not going to be any unmeasured confounding which messes up my estimate. So I have a partial manipulation for mags. That is, I can tell you in some cases what the effect of a manipulation is going to be, and in some cases I can't. Okay. Now, since we can have, so we have sort of two problems. One problem is that multiple DAGs can have the same marginal mag, but it can also be the case that there can be multiple mags that have the same independence model. So, and we say that those mags are Markov equivalent to each other. So, for example, all of these mags have the same independence model. Nothing is independent of anything, given anything else, according to this modeling. So given these different mags, what we're going to do is to create a partial ancestral graph, which is the analog of a CP DAG or a pattern. That is, it represents the set of mags, the set of Markov equivalence mags. In this particular case, the partial ancestral graph just looks like this, where these circles mean I don't know whether there's an arrowhead here or not in the corresponding mag. So this says I'm representing a set of mags. Some of those mags have an arrowhead here. Some of those mags don't have a tail here. And that's true for all of them in this particular case. So the partial ancestral graph basically says I'm going to have A adjacent to B if and only if they're not deseparated conditional on any subset of the observed variables in any DAG in the Markov equivalence class. I'm going to have A arrow B if A is an ancestor B in every DAG in the Markov equivalence class, or I could say every mag in the Markov equivalence class. A double-headed arrow B, so the arrowheads mean not an ancestor, the tail means is an ancestor, and the circle means sometimes it's an ancestor in a Markov equivalent graph, and sometimes it's not. So now I have these different kinds of edges. I can have a directed edge, a bidirected edge, a partially directed edge, and this kind of undirected edge. So that's what we're using. So we've gone from DAGs to their marginals, mags, and then we've gone from mags to their Markov equivalence classes, PAGs. So what we have to talk about now is what do we do with PAGs and how do we find the PAGs? That's what I'll do in the second part. So I think let's take a break here. So let me just introduce a data set I'll be talking more about in a minute. So this is from 1968, where Sewell and Shaw studied 5 variables from a sample of 10,318 Wisconsin high school students. They measured sex, IQ, whether or not you plan to go to college, whether or not your parents encouraged you to go to college, and your socioeconomic status. All of those were taken to be discrete and ranging from 2 values to 4 values. At the time, there were many more men going to college than women, which is reverse is the case now. So I doubt that this has anything to do with the current situation, but this was had to do with the way things were in 1968. Let me just show you some possible different maximal ancestral graphs, which you could form out of the out of those 5 variables. I'm 1, 2, 3, 4. I guess in this case, what has happened is we've marginalized out what IQ, socioeconomic. So in this case, socioeconomic status has been marginalized out. These are what you see here is that there's a directed edge from sex to college plans. Here, there's a common cause of sex and college plans. Here, we would have parental encouragement, IQ as an ancestor, parental encouragement, college plans. Here we would have that there were latent common causes of parental encouragement and IQ. And all of these would end up having the same, they would all be Markov equivalent to each other. That is, if you applied M connection to each of these different marginal graphs, you would end up with the same independence model, in which case you would see that the partial ancestral graph would be the one shown here, which has the same set of adjacencies as every member of the MAG, but differs in orientations. So everywhere that the MAGs all agree on whether or not there's an arrowhead, which would be here, sex, PE, and IQ collide is an unshielded collider, and we would see that it is still an unshielded collider in the partial ancestral graph. On the other hand, the cases where sometimes it's a double-headed arrow and sometimes it's a directed edge, such as sex to CP being directed here and here it being bidirected, means that we would put a circle there. Sometimes it's an arrowhead, sometimes it's not an arrowhead. Again, in contrast over here with this edge between IQ and college plans, in all of the MAGs, in all of the Markov equivalence MAGs, they agree there's an arrowhead, so there's an arrowhead that goes there. And down here, there would be circles because sometimes there's an arrowhead at IQ and sometimes there's a tail at IQ. So that's what the partial ancestral graph would look like. It's possible to construct it from the independence model simply by looking at the independencies. So just as in a DAG, you can use V structures to tell that there's an unshielded collider, here we can use the fact that sex and IQ are independent, but dependent conditional on parental encouragement to tell that there's an unshielded V structure here. So there are arrowheads here. The difference between this and the DAG case is that we can't tell tell whether there's a tail here, whereas in the DAG case, we would put in a tails at each end, because once we put an arrowhead on one end, we have to put a tail on the other end. That's not true in a mag. So let's see here. Similarly here, we would see that these are different marginal graphs. They all entail the same M connection relations, and they can all be represented by this particular partial ancestral graph. Could you excuse me 1 minute? Somebody's at the door. Sorry, somebody came to my door and the dog went crazy. So in this particular case, what we see is that, again, there's an interesting distinction here. In both cases, we can tell that x1 is an ancestor of x4 because there's a directed edge, and we can tell that x2 is an ancestor of x4. However, there's an important difference in these cases, as we saw earlier, because in the case where the directed edge from x2 to x4, we also know that there is no unmeasured confounder of x2 and x4. Whereas in the case from x1 to x4, we know that x1 is an ancestor of x4, but we don't know whether or not there's also an unmeasured confounder. So it turns out that by looking at the partial ancestral graph, it's possible to tell in some cases that something is definitely an ancestor, and something is definitely not an ancestor, and that you can't tell whether it's an ancestor. And similarly, you can say, in some cases where I do know that it's an ancestor, I can tell that there is no unmeasured confounder. I can tell that there is an unmeasured confounder. Actually, there won't ever be a case in which you have an ancestor relationship and an unmeasured confounder in the PAG. And there are cases where you can't tell whether there is an unmeasured confounder or not. So for those, in addition, there are cases where you can tell when there's a directed edge connecting two variables. Sometimes you can tell that, as a matter of fact, the directed path from the first variable to the second variable contains only latent variables. And sometimes you can tell that there are multiple paths between the first variable and the second variable. And sometimes you can't tell whether there are whether all the paths from the first variable to the second variable also contain some measured variable as well. So there's various features of the graph that you can use to get finer information about direct connections, no unmeasured confounding, and the ancestor relationships. Those are the sort of three kinds of things that you can get out of a PAG. And if you can tell that there is, as a matter of fact, no unmeasured confounding, that in turn typically enables you to determine whether or the magnitude of the effect of manipulating one variable on another. So even from the PAG, there are cases such as with x2 to x4, I would be able to estimate the effect of manipulating x2 on x4. So those are that's the kind of information that you get out of a PAG, and that information is information that can be used to actually make predictions about the effects of manipulations. Okay, it turns out that how do you parameterize a graph like this? That is, how do I assign parameters to the graph which would enable me to tell you what the probability distribution associated with the graph is? It turns out that in the Gaussian case, that's quite simple. Basically, it's already something that was known how to do for structural equation models. And these graphs can actually be considered a subclass of the graph of structural equation models, because structural equation models do allow you to put in double-headed edges. However, for other classes of distributions, things get quite messy and quite ugly. So if all of these variables were discrete and we were looking at a multinomial distribution, it turns out that the set of parameters that you need in order to pick out a particular distribution from the equivalence class of distributions represented by the PAG is something which has an enormous number of parameters if you have any cluster of bidirected edges which form a clique. So basically that gets to be very messy. There's it's kind of an active area of research to figure out, are there better ways of parameterizing these graphs for various kinds of distributions, and what we could do sort of non-parametrically to try and represent some distributions as well. But they can be, so for instance, in the Gaussian case, you can score them in the usual way. You can assign a BIC score, and the BIC score can be used to help select the correct partial ancestral graph. Okay. A couple other points about the partial ancestral graphs, which I'm not going to go into the gory details about. But there's essentially a kind of non-locality to the partial ancestral graphs, which is not true of either DAGs or CP DAGs or patterns, as we call them. So you may remember that for DAGs, all of the conditional independent, all of the structure that we can get out of the independence model really comes from local information around a variable. So if we want to know whether A and B are adjacent, all we have to do is to look at the independencies among A with independencies of A and B conditional on a subset of variables adjacent to A or a subset of variables adjacent to B. You never have to go far afield to get extra structural information, to get the existence of an adjacency. It's enough to just look at the local parts. That's not true for PAGs. It turns out for both adjacencies and orientations that there are features of the graph which depend upon things that are not close by to a particular variable. So I won't go through, this is an example of something called a discriminating path, and you don't have to worry about the details, but basically, if you want to know whether the WV edge collides with the YV edge, even though it's shielded, it is possible to actually determine that by looking at whether or not x and y are deseparated conditional on a set of variables that doesn't contain v. If the set of variables that deseparates x and y doesn't contain v, then you know that this has to be a collider. And you'll note that in order to determine this, I have to look at x and y, even though x is not connected to y directly by an edge and can be arbitrarily far away along some path. So I could put as many variables as I want between x and v along this path, as long as this path contains only colliders, and each of the colliders is a parent of y. So what that means is that in order to be able to ultimately construct the PAG from the independence models, it's going to be computationally and statistically more difficult to do so because we would have to condition on all of the variables along this path and then not condition on v. And so you're conditioning on a very large subset, and you're having to look at a lot more conditional independence tests in order to figure out whether there's a collider here or not. So that's with respect to orientations. You have a similar problem with respect to adjacencies. It turns out that in order to determine that two variables x and y are not adjacent, that there's some set of variables that I could condition on, which would deseparate x and y, I would have to look not only in variables that are adjacent to x to condition on, or variables adjacent to y to condition on, but I might have to look at variables which are in some sense far away from x and y in order to condition on them. Now, I don't have to look at arbitrary subsets of variables, but in some cases I have to look at a lot of different possible subsets. So both of those introduce a computational difficulty and a statistical difficulty, and they also just make it that you have to do a lot more complicated algorithm. Okay. Nevertheless, the fast causal inference algorithm is a kind of generalization of PC, which which in its initial phases looks a lot like PC. It starts off with a complete graph where I put these kinds of undirected edges between every pair of variables. And then there's some complicated stuff, but I have to search in a clever way for a set of other variables that renders the two independent. And if I find such a set, I remove the edge and I record what that set was, just like PC would. The only difference here is, as I said, it's a lot more complicated step because I have to look at variables who might be far away, and I might have to look at a much larger subset of variables. Okay, then basically, just as in PC, the first thing I would do, I would orient V structures, right? I would orient unshielded colliders, and that's what you do here. The only difference being that these stars represent that you don't know what the other end of the edge looks like. So this might be there might be a tail here. There might be an arrowhead here. It really doesn't matter. You're not going to do anything in your orientation to whatever was already here as you go through your algorithm. You're just going to leave those parts the same, but you're going to put arrowheads at gamma. So that's just like what PC would do, except PC would put in tails here because the only kind of edge that has an arrowhead in the PC algorithm is a directed edge. But here we have different kinds of edges that have arrowheads here. So this might be a circle, it might be a tail, it might be an arrowhead. We don't care what it is. Whatever it is, we're going to leave it alone and just put in arrowheads here. So this is still very similar to PC. Then we have more orientation algorithms, steps, which again look very similar to PC, but are slightly different. So here, if I have an arrowhead coming into a circle, then I make it a tail, which is similar to orienting edges away from a collider. Similarly here, if I have if I ever see this if I'm constructing my graph and I ever see this situation, and I have an edge where there's a circle at gamma, I want to put a tail there. So that's like orienting away from cycles. So it's analogous to orienting away from cycles that we did in PC. And here, this is analogous to the fourth Meek rule, the third Meek rule, whereby we had a, if we had sort of that double triangle situation, we were able to orient an edge. So each of these orientation rules is exactly analogous to one of the orientation rules in PC. But then we need a fourth rule, which says if there's this kind of discriminating path, and we have beta is in the subset, we orient things one way, but otherwise we orient it as a collider. We put arrowheads at beta. And because these discriminating paths can be of arbitrary length, this can really slow things down. And it tends to be, in practice, extremely inaccurate, because in order for it to work, you have to have correctly oriented so many different things exactly correctly that any error in that means that this can mislead you. So in practice, it's for a short discriminating path, it might work. For a long discriminating path, it's fairly useless on any kind of real data. With those four kinds of with this as my algorithm, what I can show is that in the large sample limit with probability 1, the output is a PAG that represents the true graph over the observed variables. That is, I have the right Markov equivalence class of graphs. In the worst case, it's extremely time consuming, just as PC in the worst case is extremely time consuming, because that's a case where I have a complete PAG and I would have n choose 2 times 2 to the n minus 2. And it would be extremely reliable, unreliable, because I would have to condition on so many variables, and it would be extremely slow because I would have to do so many tests, and it would be extremely unlikely to produce the right result because so many tests, some of them are going to go wrong. There are modified versions of this, which you can halt at any given order of conditional independence test. And the output is still correct, but it says, I don't know, a lot more often. So you have to slightly reinterpret what the output says to say, I don't know, more often. When every pair of variables has a hidden confounder, then the output isn't useful, because all it says is that everything is connected to everything else, and you don't know how it's connected to everything else. So if we go back a ways and we look at one of the examples we saw earlier here, sorry, did I go too far? Yeah, here right? So here, here every pair of variables has an unmeasured confounder, and then when I look at the PAG, this is all I get, and it just says I have no idea what's happening. Everything's connected to everything else. I have no idea how. I can't predict the effects of any manipulations. I can't tell you whether anything is an ancestor of anything else. So these kinds of situations, if they're in cases where you have these cases where everything has a confounder, this is what you get. And note that it doesn't tell you, this could be a single confounder of x1 through x4, or it could be that each pair has a different confounder, and it doesn't tell you anything at all about either of those situations. It just says, I don't know what's happening here. The other major limitation is that if you have a case where A is an ancestor of B and there's confounding of A and B, you're not going to be able to tell that the confounding is there. So cases where, and that can happen quite a bit, and that's quite a limitation of the algorithm in terms of not seeing confounding when you also have these directed paths. It'll just say it can't tell. The output is a PAG. It represents an infinite Markov equivalence class. The removal of the adjacencies and the orientations are no longer completely local. In practice, for some reason that I don't fully understand, it's actually much less accurate than PC in terms of things like adjacencies and orientations. So it really is something that we're working on improving, but although theoretically it sort of has nice results about what the output can pick up and what it can't, in practice it has decent precision in terms of adjacencies. It's got poor recall in terms of adjacencies, and it actually, in terms of orientations, it has both poor precision and recall. We do have a manipulation model for PAGs in the sense that there is a complete algorithm whereby if I give you a PAG and ask you to use the PAG to estimate the effect of a manipulation, it will either tell you that not all of the DAGs represented by the PAG agree on that, and so it cannot give you an answer, or it will give you the answer that they all agree on. There's another way of trying to get manipulations out of PAGs, which is similar to patterns, and that is you could take your PAG, you could turn it into every possible MAG represented by that PAG, and then use each MAG to tell you what its estimate of the effect of a manipulation is. And that has been worked out as well. So instead of getting a single answer out for a manipulation, you would get you would get a set of answers out, and you would know that it was one of this set of answers. There are some theoretical problems with doing that, which I won't go into, but it turns out to not be particularly useful in many cases. In the large sample limit, FCI will give you a partial ancestral graph whose output is arbitrarily close to correct with probability 1. But it's not uniform consistency. And what that means is that it can be at every sample size, at every finite sample size, there's some model that I can make so close to unfaithful that the algorithm will screw up and make a big error about what the actual output should be. So unless you make and that turns out to be not simply a function of the algorithm, that's a function of the fact that there isn't any algorithm which is immune to those kinds of errors unless you make stronger assumptions than the causal Markov assumption and the causal faithfulness assumption. So you really have to outlaw not only that it's exactly unfaithful, you also would have to outlaw that it's even close to unfaithful in order to be able to get something whereby the worst case was not that I would be fooled. So as your sample size increases, there's fewer and fewer models that can fool you, but because there's an infinite number of alternatives, there's always some model that can confuse you at the given sample size. Now, I mentioned the advantage of using MAGs or PAGs or FCI is that they only use conditional independence information. So we have tests of conditional independence. They can be used for many families of distributions, but it's also the case that we now have some non-parametric tests of conditional independence. And if we use those tests, then we can apply FCI quite broadly. However, and so that's an advantage of using only the conditional independence information. A disadvantage of using only the conditional independence information is that there are these other kinds of constraints implied on the observed margin that are not conditional independence relations. So there's two kinds of such constraints. Some of them are non-parametric. You don't have to limit the family of distributions. It's just a constraint on the condition on the distribution, regardless of what the family of distributions is. On the other hand, there are also constraints that apply to particular families of distributions. So I showed you earlier that there was, if we go back to, let's see here. Let's see here. Yeah, if we go back to this case, I'm sorry, I'm going faster than, I don't know how to stop it. Oh. This case here. So if this is the true graph, and we marginalize out t, then there are no conditional independence constraints, and so my PAG would simply be a complete undirected graph where every pair of variables has an edge between them with two circles on the end. However, if we take all of the distributions, the Gaussian distributions compatible with this graph, and take their marginals, in that marginal, we will always see that this constraint holds. So if I just gave you the complete PAG, it wouldn't tell you anything at all that this is about whether this is the correct graph. It would have a gazillion different alternatives. But if I looked and saw that this constraint held, and I made assumptions about that it didn't hold by coincidence, that it held because of the structure of the graph, then I would actually be able to conclude that there was actually quite a small set of graphs which were compatible with this constraint. And if I said that, as a matter of fact, none of the x's caused a latent variable, it would pick out this graph uniquely. So the advantage of just using the conditional independence relations is that it's fast and we know how to do it quite broadly. The disadvantage is that we're ignoring information that's in the distribution that we could use to narrow down the correct graphs that we choose. So it's a very active area of research to use constraints of this kind and generalizations of these constraints to help us with particular parametric families. And it's also, there are some ones that don't depend on any parametric family, which would help us narrow down what the correct graph is. Unfortunately, those non-parametric cases seem to require enormous sample sizes in order to be useful for anything. Okay. Okay, now let me say something about selection bias. And here the idea is we can again employ the same sort of bag of tricks, the cost being that when we employ this, when we have selection bias, that we get less information out at the end, because what we're going to represent are Markov equivalence classes of DAGs that have confounding and selection bias, and hence they have fewer features in common, and so there's less for us to say about what the common features are. So suppose here that I had measured sex and IQ, and that in the population, sex and IQ were independent, but that there was some college that had a biased admissions policy, so that sex and IQ together caused whether or not you were accepted to that college. And so we would see that sex and IQ are dependent, conditional on whether or not you were enrolled in that college. So for instance, if you took your sample from that college campus, you would see a dependence between sex and IQ. Now, suppose, however, I just took my sample S completely randomly and had nothing to do. So I took my sample on the college campus, but also off the college campus. In that case, it would be the case that sex and IQ were independent, conditional on whether or not I was in my sample. That's S equals 1. So I would have that sex is independent of IQ given S. And FCI would, well, I should say the correct representation of that conclusion is that there's sex and IQ, and that they have no, they're independent of each other in my sample, and I don't see any connection between them. And that's correct. Sex doesn't cause IQ, IQ doesn't cause sex, and I haven't conditioned on anything which is affected by sex and IQ. On the other hand, if my sample was selected from within the college campus, so that when I conditioned on when I looked inside my sample, that's the case where S equals 1, I would see that, as a matter of fact, sex and IQ were dependent in my sample. So what we could look for is that sex and IQ, for example, would output something like this. That it would say, well, yes, sex and IQ are dependent, but I actually don't know whether sex causes IQ, IQ causes sex. There's unmeasured confounding of sex and IQ, or maybe, and this is now an additional thing I might consider, it's none of the above, but there's selection bias between sex and IQ. So it looks something like this graph. So that's a case where I can't tell whether there's selection bias. Is there ever a case where I could tell that there's selection bias? Well, suppose that x1, suppose this is the true graph, and that my sample, you get into the sample only when S1, S2, S3, and S4 are all true. They're all equal to 1. So this is my conditioning set for being in the sample, and these are the causal relationships. These are how you get into the sample, as well as what causes what among the x's. So I've measured the x's, but I've only measured them within the S1, the S equals 1 case, where S1 through S4 are all true. What would I see when I do my conditioning? Well, what I would see is that x1 is independent of x3 conditional on x2 and x4 given S, right? So x1 to x3, I have to go through x2 and x4 as non-colliders. They block both paths, and it doesn't matter whether I condition on S1 through S4 or not. So I have that x1 is independent of x3 given x2 and x4, and analogously I have that x2 and x4 are independent of x1 and x3 when I condition on S1 through S4. So I have these two conditional independencies that I see in my sample. Those are the only two that I'm going to see in my sample. I'm going to see that x1 and x2 are dependent conditional on S1, S2, S3, and S4 because of this path here. So this is what I see in my sample. If I feed that sample into PC, what am I going to get? Well, what I'm going to get is this. It's going to say, well, x1 is, it's going to remove the edge between x1 and x3 because it saw that they were independent conditional on x2 and x4, and it would remove the edge between x2 and x4 and x1 because it was independent conditional on x1, x3, and it wouldn't see any colliders because none of these are colliders in this graph. So basically, what I would see is this as the output. Well, that's got to be wrong, according to the assumptions we make about PC. That's got to be wrong because that says that there are no unshielded colliders. And so if I try and represent a graph this way, a directed graph this way, I'm going to have to make it a cyclic graph. And that's the assumption we make as false. So if, under the assumption that the graphs are acyclic, if I ever saw this, I would actually know that there had to be selection bias somewhere. So that's the kind of reasoning that we want to use, again, within FCI to say not only can we find some cases where we know there has to be unmeasured confounding, we can find other cases where we know that there has to be selection bias. And we can sort of apply, we can redefine our PAGs in such a way that we take our original definition. So now every independence that we look for is one that's in our sample And so we've conditioned on S equals 1. So as before, where we said if we had A arrow B in our PAG, that A was an ancestor of B, here we would change it to say, well, it's either an ancestor of B or it's an ancestor of a selection variable. And similarly here, everywhere we said is an ancestor, we would change it to or of a selection variable. And then we would add a new kind of edge, which basically says if I ever see this kind of undirected edge with no circles on the end, that only occurs when A and B are both ancestors of a selection variable. So if I ever see these undirected edges, I know that as a matter of fact, I've got a selection bias. I can run the same story again where I have to complicate how I look for adjacencies, and then I have to add a whole bunch of more extra orientation rules. So for example, if I ever see an undirected edge come into an edge which has a circle at the end, then I know that what I have to do is to make this circle into a tail, where that tail now means that beta is an ancestor either of gamma or of a selection variable. So I have to add a whole bunch of more orientation rules, and some of these orientation rules are again quite non-local. So what this means is this dot 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 means if I have a bunch of undirected, if I have a path that from this variable to this variable where all the edges are circle edges, then I have to change the circles down here into tails. But this can be an arbitrarily long path. So I can run the same story again, and now I've not only dealt with confounding, but with selection bias. But the price that I always pay is that I'm slowing down the algorithm and I'm getting less information out. Before I used to say, well, this variable is an ancestor of that variable. But now I'm just saying, well, this variable is an ancestor of that variable, or it's an ancestor of some selection variable. That is a variable that I've conditioned on in order to get into my sample. So now we can consider other extensions of FCI. So basically, again, you can speed it up at the cost of informativeness by limiting the size of the conditioning sets that you look at. You can deal with missing values by performing your statistical tests only on the subset of units that have no missing values. You can also deal with missing values by performing tests on units that have all the values for the variables in the conditional independence test that you're testing, but you have to make some mild restrictions on structure. So let me stop there, and that's sort of the basic story that we have, which is we've created a new kind of graph. We've defined M separation and M connection for that kind of graph. So that means that we now have an independence model for that kind of graph. We can represent a set of distributions with that kind of graph. We have a manipulation model for that kind of graph. And we have a kind of marginalization operation that we can do on all of those models. We can marginalize the graph and get a new graph. We can marginalize the independence model and get a new independence model. We can marginalize the probability distribution and get a new probability distribution. And so what we have done is we sort of made those parallel marginalization operations match up in exactly the ways that we want. And once we've done that, we can then basically extend PC to sort of handle a lot of the different kinds of problems that we ran into before and keep weakening the assumptions that we made in order to get correct results out. The cost we have is what comes out of it is typically less informative. Okay, I'll stop there.
All right, thank you very much. I guess we can take a moment for, do we have any questions for Dr. Spirtis? Well, I have a quick question.
Sure.
So, for CPDAG, it's we have a pretty nice characterization. So
Yeah.
all the equivalent DAG basically have the same skeleton, have the same V
Right.
structures. Can we see anything about PAG, partial ancestral graph?
Yes, yes, we can. Let me see if I can get the let's see here. What am I searching for? Yeah, right here. It's actually similar, but again, computationally much more difficult. For two mixed ancestral graphs, in order for them to be Markov equivalent, they have to have the same adjacencies, just like the CP-DAG case. They have to have the same unshielded colliders, just like the CP-DAG case. But then there's this third condition. And this third condition is that if there's a discriminating path for a vertex V in both graphs, then V is a collider on the path in one graph, if and only if it is a collider on the path in the other graph. So if we go back to, I think I showed this earlier. Let me see if I can do a search on. Can't do that. I'm looking for discriminating paths here. I had a picture. Let me. Come on. Let me do. Whoops, maybe I removed that slide. So a discriminating path is a kind of path whereby all of the edges on the path, except for the two at the end, are double-headed arrows, and each vertex on the path is a parent of another variable. A particular other variable on the path. So it's not a very intuitive kind of object. And in order to check whether or not they're equivalent, you basically need to look for those kinds of paths and check whether the d-separation that holds for the two endpoints actually contains the variable next to one of the endpoints. So it's very unintuitive and somewhat costly, although quite recently people have been able to speed it up a lot. So there is a theory on Markov equivalence.
So I guess a quick follow-up is, if you are given a PAG,
yeah,
you can enumerate all the mags in the same.
Yeah, that's not trivial to do. So it's fairly fast to create one particular mag out of the PAG. But things get complicated because if you put in, because of these non-local features, it's possible that you can mess things up in sort of very unobvious ways. So creating all of the mags that belong to a particular PAG is a little messy, but I mean, it's doable. It's just a somewhat computationally expensive, but finding a mag that's in the class is actually pretty cheap.
And I guess the other way around, given a mag, you can find a PAG pretty easy.
Yeah, you can just, yeah. So essentially you can, in terms of adjacencies, there's again, looking for a particular kind of path that occurs if and only if two variables are adjacent. And you can do that quickly, and then you can just feed it into, you can use the MAG as an oracle for the FCI algorithm, and it'll just output the PAG. So you just use the MAG that you started with, and every time FCI asks a question about conditional independence, you just go to the MAG and look at M separation and then give that answer back. And that will get you the PAG.
Okay, thank you. Yeah, sorry.
So I think generally it's been, yes, there's kind of a whole analogous theory of PAGs, which runs parallel to what happened with patterns or yeah.
Yeah. It's just a drill, right? So we don't have to. Sorry, there's a fire alarm drill. Anyway, we have two more questions.
I have a question. So when you mentioned about the limitation of FCI
Yeah.
algorithm, you said that for any type of the method is gonna provide some arbitrary distance away from the true model. So for you suggest for the large sample size, or you have a lot of data, so just practice practicing the model again and again, and then hopefully after that you will find the possible model that's find the common cause. So my question is there any other ways that we can make this process more practical and then find the solutions relatively in the efficient ways? It looks like each time you practice the model, it's very computational expensive.
Well, it depends on sort of how dense the model is, how computationally expensive it is. But basically what the theorems guarantee you is that at some sample point you'll get the right answer, but it's not going to tell you it's not going to tell you what that sample size is, and it's not even going to be able to. So the real worry is that there are things which are close to unfaithful. And as long as you have things which are close to unfaithful, in the Gaussian case, there's nothing you can do about it. It's going to be the case that you can't tell the difference. In some other classes of distributions, then there's more information in the data than just the conditional independencies. But the only thing, I don't think there's any way to guarantee that you don't have some, the worst case would be, for instance, every variable is connected to every other variable, but that unfaithfully it looks like a simple graph. And once I allow myself to connect every variable to every other variable as an alternative, and to put in as close to conditional independence as I want, then at a given sample size, right, I can always, no matter how large that sample size is, I can make my fake model, or I can make the model that's completely connected look like the simple model, simply by getting closer and closer and closer to the conditional independencies that are entailed by the simple model. So if what you're interested in is uniform consistency, the only way to get it is to have some stronger assumptions. Otherwise, and they're just, I mean, it's not a feature of the algorithms, it's a feature of the assumptions that there is no way to eliminate those completely connected models which are arbitrarily close to mimicking the simple models. That's a feature of the assumptions, not of the algorithms.
Thank you very much. Hello.
Yes.
Oh, okay. Okay. Yeah, that's great. Yeah, thank you. Yeah, I got one more question. It's kind of follow-up questions. So since it is, well, the FCI is performs relative good for the Gaussian distribution, but it's not so good for the non-parametric. So is that something that in between, for example, we only assuming for like exponential family only using like or other things to offset the problem of non-extremely non-parametric case?
Well, I think in the non-parametric case, it has a lot of the same problems that PC does. So, I mean, as long as your tests are good, you know, the output of FCI will be good. The difficulty is that if you're is that the power of the tests, if you're conditioning on a large set of variables, in the non-parametric case, is often poor, and it's also computationally expensive to have large conditioning sets. So I don't think it's a particular problem with FCI so much as it sort of needs better tests. I should say that even in the Gaussian case, as I said, for reasons I don't quite understand, its performance, it's a much more complicated algorithm than PC, and there are a lot more steps, places where it can go wrong, and that seems to affect it with respect to orientations especially. So that's something we're working on, but it's proved to be a somewhat stubborn problem.
All right, thanks. If we don't have any more questions, let's thank our speaker again. Thank you very much, Dr.
All right, thank you.